All right. Let me get started here. So I'll begin with a word of prayer. Heavenly Father, we thank you for this day. Again, I thank you for calculus. Help us to understand a little bit more about calculus today together. Again, I just pray the students will be encouraged if they're struggling just to do their best, Lord, each day for your glory. In your name I pray, Lord Jesus. Amen. So, yes, as I was telling you guys a second ago, we are now in chapter 5. And so today we're talking about something called Fermat's theorem. Well, no, it's not Fermat's theorem. That's something else. Is it Fermat's theorem? I guess Fermat's last theorem. That's the interesting one. This is a slightly easier one. And so I need to talk to you basically about local and global extrema. So the big topic we're getting into here is graphing with calculus. All right, so like, oh man, we have done snippets of this up to this point, right? Like we have done what? Like we found some tangent lines, right? And so every time we find a tangent line, that's giving you some kind of information about the graph of the function. So we want to do a lot more than that. So where we're going is to understand how to make a pretty faithful graph of a function based on the information that we can glean about the function using calculus. So in particular, we're going to see that there's a couple of main concepts that we want to understand. We want to understand how to decide when a function's increasing, when a function's decreasing. We're going to learn about something called concavity. Function can be concave up or concave down. Concave up means it's kind of like bowl-shaped, so it's like a U. Concave down means it's kind of like an N, so like a bowl upside down locally. And we'll see that differentiation shows us all these things. But probably the first thing you want to learn about graphing when we get past continuity, which we've already talked about, right? Is the concept of when functions like biggest or smallest. So these are called extrema. And so just give you an example. So if I have a function and its graph, let's say, looks like this, all right? And let me pick some points here. So here we've got y equals f of x. We're going to say that this point is -4, -1. I'm going to tell you the coordinates right there are like, let's say, 3, 10. And this guy right here is, let's say, 20, 12. All right? So let me talk about it. So here, the domain of the function is what? As it's given, apparently, -4 included to 20 not included, right? And yeah. So some things I can tell you. F of -4 equals to -1. This is the global minimum value, right, for the function, right? And what else can I tell you? I guess I need to give you, so you guys tell me what the points should be here. I'll let you guys pick it. It's somewhere between 10 and 20, right? Like maybe 15? All right, so 15, I'll let you do that. And maybe that's at like 5, all right? Okay, so that's the global minimum value. The global maximum does not exist, right? I'd like to say that this function has a global maximum of 12, right? But I can't say that because it doesn't actually attain the value, right? Like here, that open circle means that like f of 20 does not exist. So, you know, I'd like to say that f of 20 equals to 12, that's the global maximum, but 20 is not an element of the domain. So I can't. All right? So a maximum or a minimum for a function, it has to be, the maximum or minimum value refers to the y, right? Where it's at is the x. All right, so on the other hand, I've got two other things going on in this, right? So these 2 points here and here are examples of what are called local extremas, right? So we also can say this. There is a local max at x equals to 3 of f of 3 equals to what? 10, right? And there's a local minimum at x equals to 15 of f of 15 equal to 5, right? So what does it mean to have a local max or a local min? How would you define this carefully? So like definition, C is local max of f at, let's say, x equals to a if, you know, f of x is less than or equal to c for all x near x equals to a. Now we could make that more precise, right? You could say that there exists a open set around the point for which that's true. But that's basically it. C is larger than the values of, C is, you know, I do need, I'm missing something here. Sorry. What do I need about C? C has to be what? C is equal to f of a, right? So that's a local max. Likewise, local min. So I could write it this way. f of a equals to, let's say, C is local minimum of f at, you know, at x equals to a if f of x is greater than or equal to c for x near a. And if it's either a minimum or a maximum, we say that it's a local extrema, right? A local extrema means either min or max. Okay? So that's the first thing. Another example. What if our graph looked like, let's see here. Whoop. So here's y equals f of x. So my question for you guys is, So for this one, what do you guys think? Does this have a global minimum? Does it have a global maximum? Does it have any local minimums, local maximums? What do you guys think? A local maximum? Local maximum where? Local maximum is 6, right? The value of that local maximum is 4, right? It has a local minimum of 2 at 5, right? It has neither a global maximum nor a global minimum, right? Because it is true that 0 is less than f of x, but there does not exist c, or let's say there does not exist a in the domain of f such that f of a is equal to 0, right? So while 0 serves as what's called a lower bound for the function, it's not attained by the graph, therefore it's not the global minimum. Okay? Are we good? Yes, no? I would like to think about maximums and minimums. They could also happen on the edges of things, right? So like, for example, if I had something like this, suppose we got -3, 4, over here to 5, 6, I guess, I don't know, whatever. And this point maybe is 2, 1, right? So if that's the function, the graph of the function y equals f of x, for this one, we can see that the global maximum is, the value of the global maximum is 6. It's attained where? At 5, right? So like f of 5 is equal to 6. That's the global max. Global min, f of 2 equals to 1, right? This is the global minimum. But I would also say that, it's always going to be true that a global maximum is also a local maximum. See, because to be a local maximum just means you're the biggest near the point. To be the local minimum means you're the smallest value the function takes near the point, right? So any global maximum or global minimum is always going to be likewise a local min or max. But I would like to say here that, f of -3 equals to 4 is a local maximum. Okay. All right. So I think I've said enough about that. Usually nobody gets confused about the concept of min or maximum in that way, right? So yeah. So there's something called the extreme value theorem. Sounds like something that you'd find on the X Games or something, right? This here theorem, extreme value theorem. Very, very politically incorrect at this point in time. Yeah. And it simply says that if you have a function which is continuous, f is continuous on the closed interval a to b, then there exists, let's say, c1 and c2 in the interval a to b for which f of c1 is less than or equal to f of x is less than or equal to f of c2. So this is your minimum, and this is your maximum. In other words, the extreme value theorem says for a continuous function on a closed interval, you will attain your minimum and your maximum. It's inescapable. That seems really obvious, doesn't it? Like if you think about what's the graph of a continuous function look like? This is like completely unsurprising, right? What does a continuous function look like? If this is A and this is B, you talk about a continuous function, what's the graph look like? Straight line? Well, it doesn't have to be that. a line that never ends, right? So I have to satisfy the vertical line test. Oops. I have to satisfy the vertical line test, but, you know, right? Like, I don't know what it does. It could do all kinds of crazy stuff, but if it's continuous, it can't jump, right? And so it can't do like what's not allowed. But here's a discontinuous function, right? It could do like this. Jump. You know, boop. You know, you could do like asymptotically down to there and then jump back up here. So if that was your rather silly discontinuous function, it's got neither a global maximum nor a global minimum as is available. I mean, if it's discontinuous, you can do all kinds of crazy stuff. You don't know if it's going to attain the max or min, but if it's continuous on a closed interval, you attain the maximum minimum. This is the extreme value theorem. So the kind of irony is, much like the intermediate value theorem, which is just intuitively obvious, right? Like the intermediate value theorem, we drew similar pictures, right? If you have any value that's between A or B, you draw a line, you have to hit some point C in between where you attain the value, right? Both the intermediate value theorem and the extreme value theorem are actually quite technical to prove because they're ultimately really theorems of topology, which is the more deep study of continuity. Anyway, my little brother wrote an article about this for teachers a few years ago, about the topological nature of this part of calculus. But anyway, we don't need to prove it. We're just going to use it. I give you a reference in the notes to a book by a mathematician known as Apostle. And Apostle's calculus was the calculus book which sort of more somewhat elite universities used in the late 60s, early 70s when we were trying to test our might against the Russians. So it's from a simpler but more brutal time. The Apostle calculus book is, if you're a really good student and you want like a second book to read in calculus, Apostle is a good thing to look at. It starts with integration and then does differentiation second, which is weird. Well, we don't know what integration is, right? What am I talking about? Okay, so moving on here. Definition. This was an important one. Given function, f, we say c in, I got to be careful here. All right, so technically C doesn't have to be usually the usage here is C, let's say a limit point of the domain. I think that if you look at the definition in my notes, it's a little bit actually ambiguous. I don't really come out and say this, but I think to make this interesting, see, a limit point in the domain of F is a critical number for F if either f of c is equal to 0 or f prime of c does not exist. I don't mean to say f, excuse me, my bad. I'm missing something. I warned you guys I would make mistakes today, didn't I? Physics burnt my brain yesterday. I'm still recovering. Yeah, you guys know physics is hard, right? Yeah. You're like, well, this course isn't easy compared to physics. this course is easy. Anyway, so I digress. So either the derivative is 0 or it's undefined. This makes what's called a critical number. And if c is in the domain of the function, then c comma f of c is critical point. So a critical point is a point on the graph which corresponds to a critical number for x. Man. Oh well. So let's look at an example. Example 4. So let's see here. F of x equals to 1 over x. All right, so we've got f prime of x is equal to minus 1 over x squared, right? Do you guys remember what I meant by limit? Limit point just means that the domain is defined near the point. There's like infinitely many points in the domain close to the point in question. So here, what's the domain of f? Basically, you got what? X such that what? X is not equal to 0. And notice that f prime of 0 does not exist, right? It's not even defined, right? So for this function, 0 is a critical number. So c equals to 0 is critical number. But there is no critical point on the graph, right? Because 0 is not in the, I can't plug 0 in. It's not a critical point. Critical number, but not critical point. See the difference? Example 5, well, maybe we'll see the difference. Did I remove the camera? I think I went back. Yeah, I think I did. Yeah.
I want to go over our test next Monday.
Oh, I might go over the test today. Did I scan it? Solution to it? I think I scanned the solution to it. Let me set myself an alarm. We'll go over the test at 10, okay? However far I get in the new material I'll get, but at 10 we're going to stop and look at the test, okay? Actually, let me make it 9:55, make sure I got enough time to talk about the test. If I can set this alarm. Thank you for that question. That's very helpful. All right, I got 10 minutes. So I should warn you, like the next about 2 or 3 lectures, there's a lot of theory, but this is theory you need to learn and understand so you can apply it. And so we got a lot of definitions in the next couple of lectures. You're going to have to like learn the definitions and how to use them and so forth. Okay, so example 5. If we have, say, f of x equal e to the minus x cubed, what's the domain for this one? It's just everything. Everything's in the domain. That formula works everywhere. Does this function have any critical numbers? Does it have any critical points? Well, let's calculate. df dx is minus 3x squared e to the minus x cubed, right? So if I set that equal to 0 for critical numbers, right? When is that 0? Well, the exponential is never 0. So this implies x equals to 0 is only critical number. And in fact, 0 comma e to the minus 0 cubed, also known as 0, 1, this is a critical point. All right. In about 3 classes, we should be able to graph this pretty well. We're not quite there yet. So guys, why are we interested in critical numbers? We're interested in them because if you think about it, well, let's look at example 6. This one caught you guys off guard on the test. So f of x equals to, let's say, the absolute value of x. All right? So a formula for that is the square root of x squared. So that's how it came to you on the test, and nobody really noticed this. Because the square root of x squared is not x. It's the absolute value of x. And so when I differentiate that, how do I differentiate it? Well, df dx is equal to d dx of the square root of x squared. And so that's, well, 1 over 2 square root of x squared times d dx of, well, x squared. So what you got? You got yourself 2x over 2 times the absolute value of x again. In other words, you got x over the absolute value of x. Now if you look at that, that's equal to 1, minus 1 rather, if x is less than 0. And it's equal to 1 if x is greater than 0. And by the way, f prime of 0 does not exist. Why is that? What's the deal with the absolute value? You guys know it? It's got a corner in the graph at the origin, right? So right there, the derivative doesn't exist. But what is that? What is f of 0 for this function? It is exactly the global minimum, right? So the global minimum for this function happened where what? Where the derivative doesn't exist. On the other hand, you guys probably already have some idea for if a local maximum, think about this, if we have a local maximum or a local minimum and the derivative does exist, what can you say about the tangent line at these kind of points? What can you say about the tangent line at every local min or local max? What's the slope of the tangent line? 0, right. So the reason we're interested in critical points is critical points are indicative. They are suggesting to us where we might find a local minimum or local maximum. Yeah? Now, do you have to have a local maximum or local minimum at a critical point? Is it necessary? Let's look at an example. Let's think about this a little bit. I don't think we're going to get to Fermat's theorem today, and that's okay. I'll do next class. We'll do that. So Fermat's theorem and Rolle's theorem and the mean value theorem, these all kind of go together. So we'll probably cover those Monday. Example, where was I? Example 7. Let's look at f of x equals to x cubed and g of x equals to the cube root of x. Both of these functions have domain what? It was close. What's the domain? All reals, right? What's the derivative? 3x squared, g prime of x, 1/3 x to the minus 2/3, aka 1/3 times the cube root of x quantity squared, right? What are the critical numbers? Here we have f prime of 0 equals to 0, so 0 comma 0 is in fact a critical point. Here we have g prime of 0 does not exist. So in fact, 0 comma 0, also a critical point. Isn't that funny? You can have a critical point where the derivative doesn't exist. I mean, the function exists, but yeah. And why are these critical points? Is it a local max? Is it a local min? What's the deal? Let's graph, right? So the graph, how's it go? It's a cubic, right? So the cubic looks like sneak snake. Comes in here nice and level. Comes out like that. There we go. There's y equals x cubed. There's the critical point. It's got a horizontal tangent line, but that is neither a local maximum or a local minimum. All right? So just because you have a critical number doesn't automatically mean that you've got a local max or min. It may be something else. It might be, sometimes we call this kind of point like a saddle. What's the graph for the cube root look like? It's the same sneaky snake, but it's put sideways, so like a so. Wee, wee. All right, like that. There's your y equals cube root. Here's your critical point. Why was it a critical point? Because it's got what's called a vertical tangent, right? The derivative actually goes to infinity in the limiting sense. It's neither a local maximum nor a local minimum because you got values below it and above it, close to the point. So this is another way that a critical point could fail to be at a local max or min. Any questions? So like Fermat's theorem says, that's the next thing we'll cover. It says that if f has a local extreme value of f of c and f prime of c exists, then the derivative must be 0. So the Fermat's theorem gives you a partial result in this direction, but we already know that the converse to Fermat's theorem can't be true because there are places where we have critical points and yet don't have local max or min. But anyway, that's what we'll start. That's what we'll pick up next class. Let me hand back your test to you guys. I will not name names as the camera is running. In the, I don't always look at the solutions in here to the tests, but I think we got time today, so let's do it. Let's see here. See if I can open it. Come on. Well. Ah, it's hiding. I found it though. See if it'll work today. All right. It's you. I don't think I know everybody's name, but I know some of you. Let's see here. Ah, good catch. Let's see here. What would you like your name to be today? All right, let's get that for you. So, Christian, let's go. There's yours. And you. Aw, man, I need to make a bigger test. What was your name? Oh, yeah, I haven't graded yours yet. I'm sorry. And yours? All right. Let's see here. I'll find it eventually. Everybody here got their test? Okay. So, as a general point of order going forward, I think everybody should be here every day. Like, about half the class is missing right now. Given the performance on the test, I don't think that's a reasonable thing to be doing, almost without exception. Everyone should be here and should be thinking about things and should be working on calculus because you need to work on calculus. Now, let's just go through the test right quick. So we have, I probably should move the camera. almost without exception, everybody got problem 1 right. I mean, some people like didn't quite pick up on the differentiation for like the second part there, but for the most part, you guys got that one. Let's see here. If you didn't get problem 1 right, that one is certainly the easiest one to fix. And the other thing I would say, so just to be clear, let me say this going forward. I need you to write things as I write them. Let's just say that, because I've tried to communicate. There are other ways to like write your work, but I'm still seeing a lot of like not quite correct work. So like as a general point of order going forward, let me just say this. You should write things as I'm writing them. I was talking to Dr. Sprano, and that's what he said. He told his class, and I said, you know, I always don't say that because I actually have a lot more freedom in mind for how you could write things, but I don't mean to give you license to write things incorrectly or, you know, unclearly. And so it's probably better for me just to say, I expect you to write things as I write them, pretty much. Now, anyway, so the second one, the derivative of that is just that's a constant, so it differentiates to 0. And here, like x squared over x to the square root is x to the 3/2. X over root x is 1/2 power, divided by root x is minus 1/2 power. And then I can just do power rule 3 times. Now, many of you did the chain rule, and not the chain rule. Many of you did the the quotient rule, and you were successful. You did it correctly, and I didn't take off points, and that's fine. However, if I changed this word here, simplification not expected to simplification expected, you would have been in trouble. Because I'm not convinced that the people who did the quotient rule would have known how to simplify. Some of you would, some of you wouldn't, all right? Like, I don't know. But you really shouldn't need to use the quotient rule there. Like, I don't know, maybe that's the right way for you. I don't know, but let's just say this. You should try to understand what I did here. Think about doing it that way. Problem B, some of you didn't notice it's ddb, so b is the variable here. As I set up here, if the more than one variable is present in an expression, you may assume the variables are independent, which is to say that x, c, and a here are constants with respect to b, which means that this differentiates to 0, that differentiates to 0, this differentiates just to x, because db is 1 and the x pulls out. So the answer here is just x. So, sorry if you missed that one. There was homework like this. Problem C, I have really, listen, I have a bunch of different answers here just so that I could, as I was grading, I could try to make sure I saw your answer as being correct or not. I'm not saying you need to have all this work. There's like, this is a perfectly fine answer. That is a perfectly fine answer. And so is this and that. Like, I'm just writing different answers for myself for the sake of grading. Don't misunderstand what I'm writing here. So like, this is a product, so we gotta do product rule, but we also have to do chain rule. Like 1 minus 3x to the 6th power, pull down the 6. Notice that there's also a minus 3 here. I think about 1/3 to 40% of the class doesn't have the product rule really pinned down yet. At least on this problem, you were doing stuff like I saw some people like differentiate f and then forget to multiply by g, and then differentiate g and forget to multiply by f. Some people just wrote like the derivative is f prime times g prime. This is not true. Yeah?
I had a question about letter A.
What about A?
How did you get x to the 3/2 like it's x squared in the first? How did you get your x elements to the x?
Oh, because x squared over the square root of x is, you know, what is x squared over the square root of x? So this is like, you know, x to the 2 minus 1/2, which is x to the 3/2. That's where that's coming from, but that's fine. I think a lot of people got part D right, which is good. So that's just chain rule basically. We've got the 1/2 power So if 1 over 2 times the square root of the inside function multiplied by the derivative of the inside function, which gives you a minus here. So yay. All of you are working. Like everybody who took the test has put work into the course. Just some of you are not where you need to be yet to be competent in differentiation, unfortunately. And you do need to get competent in differentiation before the end of this course. Like that's one of our main, calculational check marks, let's say. So now listen, you got part E wrong. That's okay. I think I could understand why you might not have noticed the derivative of the absolute value function. Like it would be easy enough to have missed that. I do think there was a problem on the math battle concerning this issue. But if it looked to me like you're doing things right, but you just weren't aware of the fact that the square root of x squared is not x, it's equal to the absolute value of x. I think I only took off like 3 points as opposed to like taking 5 points off, which is kind of more, that means you're further from the truth. So if you had operated correctly here, but simplified the square root of x squared as just x, then I think I gave you just like, I only took off 3 points as opposed to taking off 5. Each one of these is worth 7 points because there's 63 total points, and 7 times 9 is 63. So, yeah. But anyway, it's a chain rule. So you've got the cube root of this. So I do 1/3 inside function to the minus 2/3 power times the derivative of the inside function, which is, 1 plus 2 over x over root x. I mean, x over absolute value of x, as I was just talking about back in example 6, right? Now here, I think, I don't know, like just bad things happened here. You guys need to work on properties of natural log. Like you're not quite there yet. You need to review properties of natural log. Natural log of a plus e to the bx plus c is natural log of a plus the natural log of e to the bx plus c. But that is bx plus c, since natural log and exponential are inverse functions. But remember, at the start of all this, I said that if you've got variables other than the differentiation variable, they're supposed to be assumed to be constant. So the derivative of a would be 0. Derivative of natural log of a would be 0 as well. And this just differentiates to b. This one here, chain rule. So you've got cosine of the inside function, derivative of the inside function, which gives us 3x squared minus 14 times the sine of 7x, cosine of stuff. Things that are just absolutely wrong. If you find yourself just writing like cosine with nothing in it, sine with nothing in it, I saw some of that. That's not going to work in here. ddx equals something. We talked about this. This is not something we should see written on a calculus test. We take ddx of an expression equals another expression, that sort of thing. We don't write ddx equals to expression. That's not a reasonable math notation. Now, let's see here. Anyway, I was going to say, part G. A lot of people got part G right. That was I would say a victory for the class overall. But many of you got it wrong. But there were a lot of people who got it right. Inverse sine. I think a lot of you guys are not quite on the same page as me in terms of what is the derivative of inverse sine. It is 1 over the square root of 1 minus the argument squared times du dx. That's the chain rule for inverse sine, if you like. Here u is 3e to the x plus 2, which differentiates to 3e to the x, and then I've got this. I don't expect you to FOIL it out. One of you FOILed it out, but you didn't do it right either. You lost a point there. Maybe not one of you. That person's not here. Okay, so many people are not here, so that's not a FERPA violation, right? Yeah. You guys don't actually care about FERPA violations, do you? No? I personally think we should bring back public shaming. Yeah? Like when I was in school, I took a test and then I could like go see my name and like score on a sheet outside the classroom, something like that. Sometimes it's like, ooh. Although even in my day, like that kind of information was starting to be guarded. When one of the professors here was in elementary school though, he was motivated to do his best work on his math class because he didn't want to wear the dunce cap to recess. Like the kid who's doing the worst has to wear this like stupid hat on the way to walking to recess. You don't want to wear the hat, right? Would that be motivating? I don't know. I don't want to resort to such tactics. So I did take a class once with a guy who handed the test back in the order of the grades, highest to lowest. That was fun. there inevitably would be one guy saying to the other guy, "Ha! Look, you look at your test," and the other guy would be like, "You didn't get your test back yet," and he'd be like, "Ah!" It was amazing. So stupid. This one here, it pays to simplify before you differentiate. If we multiply this out, the 4x and the minus 4 cancel. We're just left with x squared, which just gives us x to the minus 1/2, which gives us this. I think like 2 people got this actually simplified correctly. Many of you have done many things here which are partially correct. You know, I told you this was one of 3 possible proofs, so yeah, there's that one. This one here, you cannot take the natural log of this. You can't just take the natural log of this because there's a sum here. You have to divide and conquer. You have to differentiate this and differentiate that. So we should like call this something like W, and then make the natural log of that, do the usual implicit differentiation, and then come back and put it together. A few people got this right. Many people got it wrong. Most people who got it wrong, they took the natural log of this and assumed that the natural log of a sum was the sum of the natural logs. That's just not true. Like, natural log of a sum is nothing nice. Here's our logarithmic differentiation problem. I think a lot of you got that right, which is good. Implicit differentiation, I think the most popular mistake here was not to sort through the chain rule. See, because we've got x plus y cubed, 3x plus y squared times the derivative of the inside function. Derivative of the inside function is 1 plus dy dx, because derivative of x is 1. Derivative of y is dy dx, and then solve for dy dx. I did have a few people get this correct. Many of you wasted a lot of time and effort and energy by multiplying this out, which is just not a wise move. Like, you shouldn't multiply that out, you should just differentiate. Multiplying it out did not give you any insight and caused you to make an arithmetic mistake, I believe. Problem 7, I am very generous with in terms of if you were like partially correct, I give you some points. Now, I obviously did not give you a lot of points if you just plugged it in your calculator, which I can kind of tell if you did that. But anyway, so this is the linearization. It ends up being 2 plus 1/32 x minus 16, which gives us the approximation of 65 over 32 for the 4th root of 17, which is pretty close to right, actually. This one is not differentiable because it's not continuous. And many of you saw that, and that was wonderful. Like, a lot of people figured this problem out, which was great. And finally, problem 9 is just related rates. It worked out to 3.5. I know you guys got to go, so I'll finish up here. Problem 10, everybody should have got problem 10. Come on, guys. We did like 6 of these in class. I gave you the 4-step process. 1, right, y equals the inverse function. 2, take the function to both sides. 3, differentiate. Step 4, solve for dy dx and simplify. Answer. Some of you are thinking inverse tangent's 1 over tangent. This just is not the case. And then finally, problem 11, if you differentiate an exponential times a polynomial, what you get is a polynomial times an exponential. If that's 0, it only can be 0 if there's a polynomial, which is 0. And if you think through that, fundamental theorem of algebra says that an nth order polynomial has at most n zeros. So the answer was there could be at most n horizontal tangents in general. There might be none, but there could be as many as n. But of course, that was the bonus question, so.